Hi, everybody. Researching iOS internals and iOS vulnerabilities is hard, right? You know what I mean. My name is Jonathan Afek, and welcome to the talk Simplifying iOS Research, Booting iOS on QEMU. I gave a similar talk about this project 2 months ago at Black at Europe, and I'm happy to say that in the short time between the conferences, we were able to implement a lot of new exciting features. I'm excited to be here and present this project to you. I want to thank you all for being here and for attending this talk with me. Let's begin. All right, so in this talk, I will present a new simple way to research iOS. But before we get into this new way, let's review the current research methods used by iOS researchers. So what are the current ways researchers use in order to analyze iOS? There's a company which offers full iOS emulation on their remote servers for their customers. They have full debug capabilities, they offer many research features, and they have a solution for many iOS versions on many iOS devices. Now, this sounds great, right? Well, it is great, but there are three issues with using it. The first one is that you must be invited. It is not generally available. The second one is that it costs a lot of money to use their services. And the most important issue is that your private research, which possibly contains sensitive research details and vulnerabilities, is exposed to anyone who can gain access to the servers. Another method used by researchers is to use development-fused iPhones. These are iPhone devices made by Apple with full debug capabilities used by their own OS developers, so they could be able to debug their code on real iPhone devices. Recently, Apple also announced that they're going to provide such devices to select few non-Apple iOS security researchers in order to assist uncovering iOS security vulnerabilities before they are used by offensive hackers. This is also great for research if you can get your hands on such a device, but unfortunately, they're very much unavailable. It is very hard to get one. And even if you do get one, you probably had to do something illegal or at least make an Apple employee perform a serious breach of contract in order to get one. Plus, using physical devices for research does not scale very well. Another method used by researchers is to use checkmate demoted iPhones. Thanks to the great work by Axiom X and the team who worked on the project, now most iPhones up to iPhone 10 can be demoted and debugged as if they were development-fused iPhones. This is very good for research, but the equipment required to do this costs a lot of money. Changing the file system, device tree, the kernel, and other aspects of the system is more complicated than with emulation. Implementing fast state restoration is harder on these devices than with emulation or virtualization. And it is hard to perform research and fuzzing at scale while using physical devices. Another method used by researchers is to use jailbroken devices. On jailbroken devices, you can execute arbitrary kernel code, and recently Brandon Azad and Ian Beer published projects which enable debug capabilities on some iPhones using vulnerabilities. This is also great for research. But unless you use this kernel debugger, then executing kernel code is far from full debug capabilities on an emulated device. It is also more challenging to scale such research while using physical devices and conduct fuzzing campaigns with fast state recovery. And most importantly, it requires a vulnerability to jailbreak the iPhone or to use this kernel debugger. So in most cases, it cannot be used to research the most recent iOS on the most recent iOS device. And another method is to use regular non-jailbroken iPhones. Now, these iPhones are very easy to get, but they are very limited in their debug and research capabilities. In most cases, all you have is a crash report that looks like this. Now, this gives a lot of information regarding the status of the CPU and the registers when the panic happened or the vulnerability was triggered. But still, it is very hard to work with, and it is much more difficult than working with a full kernel debugger on an emulated system. My goal in emulating iOS was to create a new, open, free, easy-to-use way to privately research iOS without requiring any vulnerabilities. And it is very easy to start using it. Emulation lets you have full debug capabilities. It is easier to develop support for more iOS versions, and you can run multiple instances easily at scale for debugging, research, and fuzzing. Before we get into the research details, let me tell you a little bit about myself. So, my name is Jonathan Afek, and I manage the Aleph research group at HCL AppScan. When I started this role, I wanted to start getting into iOS security research. While studying the subject, I realized that there was no easy, public, open way to research iOS internals and vulnerabilities. This is when I started looking into emulation. I thought that if iOS could be executed on QEMU, then I could create such a research platform that is easy to use. I looked it up to see if anyone started working on emulating iOS and found a few very old projects that are not relevant for current versions. I also found another project that started working on executing iOS on QEMU and reached some very interesting milestones. This is the amazing work I found posted on the Worth Doing Badly blog by Chu Wei Chung. All right, so I'm not going to explain what QEMU is, but the important thing to note is that QEMU supports emulating ARM64 architectures, and therefore it is a great project to start from when trying to emulate iOS devices. So before we get to our research, let's review what was achieved by Chu Wei's project. So they chose to work on to use iOS 12 beta 4 for iPhone 10. They extracted the kernel image and the device tree from the software update available on the Apple servers. They patched the kernel and were able to load the patch kernel, the device tree, and the kernel boot arguments into the emulated device's memory. They were also able to load the ROM disk into the emulated memory. And they were able to emulate a UART serial device where they were able to make the kernel print the kernel logs and see the kernel logs on this emulated UART serial device. They booted the kernel up to the point where it executed launchd, the first user mode process, but no non-Apple executables were executed on top of it. Now here you can see the system serial output, and in the output you can see that launchd was actually executed and produced output. So what were our goals when starting this project? We wanted at first to boot the kernel on QEMU without any patches, and we did just that. But as I will soon present, we decided to patch the kernel for a feature I will talk about later. We wanted to support different hardware devices, disk, display, touch, and everything else. We wanted to support different iOS versions for different iOS devices. And of course, the main motivation for starting this all was to conduct iOS security research. Plus, we wanted to learn a lot about iOS and QEMU internals while working on this project. So what is the current status of our project? As stated before, we are able to execute the kernel and the secure monitor without any patches. But we decided to drop the secure monitor and patch the kernel for a feature I will soon present. And we're able to execute our own user mode applications over launchd that are not signed by Apple. We're able to run an interactive bash shell on iOS on QEMU. We have a few GDB scripts that allow us to list the tasks, the threads, the allocation zones, and information about them. And we also have a GDB script that allows us to switch between threads in the kernel. We currently allow access to the kernel task port from user mode. We're able to mount the full disk images from the software update with our own block device driver. And the system runs most of the iOS user mode services that come on the full disk images. We're able to connect to a Dropper SSH server running on the iOS guest, and we're able to connect it from the QEMU host. And we're able to make the kernel render its log messages to a textual frame buffer and display this frame buffer in a QEMU window. We currently only support iOS 12.1 for iPhone 6s Plus. All right, then now let's see a short demonstration of our project before we talk about the research details. All right, so this is the command line that we use in order to execute our project, our QEMU, to emulate the iPhone. Let's fire up GDB and attach it to our QEMU instance. And we can see now the kernel logs and the kernel booting. And we can see now the launch D logs and all the iOS services starting. And we have an interactive bash shell. All right, so now let's connect to the SSH server. And we now have an interactive bash shell over SSH. And we can see that we are running as root, and we can extract some host information. We can get information about the loaded kernel extensions. We can get some virtual memory statistics. We can get some more host information. And we can get a full dump of the IOKit registry. But more important than that, we can go back to GDB and, for example, load one of our GDB scripts. Now, this script is used to list all the currently running tasks, and then we can see now that we have our TCP tunnel running, we have Springboard running, and we have the Dropper SSH server running, and we have a lot of tasks running in the system. But even more important than that, we can just use GDB to debug the kernel, to use all the known and familiar GDB features and the known and familiar GDB interface to just debug the kernel as we would debug anything else in GDB. And another short demonstration, just this time we start the project again, but we have the kernels now rendered in a frame buffer, the kernel logs rendered in a frame buffer. We can display this frame buffer in the QEMU window, and we even get the bash prompt in this window. All right. So we talked about interesting past research done for executing iOS on QEMU. In this talk, we're going to walk through some select research stages we had to go through to achieve iOS execution on QEMU. We will first talk about how we were able to boot the kernel, then talk about how we were able to run executables that are not signed by Apple on the emulated iOS device. After that, we will talk about how we executed bash on iOS. Later, we will talk about the new content, getting access to the kernel task port from user mode, connecting to a Dropper SSH server on the guest from the host, rendering the kernel logs on a textual frame buffer, using our own block device driver to load the full disk images of the iOS system, and some LaunchD craziness we encountered. Finally, we will talk about what lies ahead for this project. All right. Then how did we put the iOS kernel on QEMU? This subject will be covered here only briefly, since we need time to talk about the new feature and because, as we will later see, we no longer use the secure monitor. Then I will not go on into all the details here. The Black Hat slides where this is covered together with these slides will be uploaded in a few days to a GitHub repository, and the details can be found there and on our blog. Then again, how did we boot the iOS kernel on QEMU? So we started off with the method used by Chu Wei's project. We loaded the different sections of the kernel into the emulated device's memory and started executing the kernel at its entry point in exception level 1. But soon enough, we hit a crash when we're trying to execute the secure monitor call instruction. So what is a secure monitor? Somewhat similar to the protection rings concept in x86, in ARM we have 4 exception levels. The user mode code runs in exception level 0, the kernel in exception level 1. We don't have code for exception level 2 in our system, but it is used for hypervisors. And the secure monitor runs in the most privileged mode, exception level 3. All right, so this is how the secure monitor works on iOS. So the secure monitor starts its execution at boot in exception level 3. It resides in a secure memory location that is not accessible to kernel code. It services secure monitor calls from the kernel. This concept is somewhat similar to how the kernel services system calls from user mode applications. And it is responsible for KPP, kernel patch protection. So KPP protects the system, so even if a hacker is able to exploit an arbitrary write vulnerability in the kernel, KPP is supposed to stop them from changing or patching the kernel code, the kernel page table, and other important data structures. So how did we overcome this? How did we execute the secure monitor call instruction? So we decided to load the secure monitor image in the secure memory of the emulated device. And we also loaded the secure monitor boot arguments into this secure memory. And we started executing the secure monitor at its entry point in exception level 3. The secure monitor finished its boot sequence and jumped to the kernel at its entry point in exception level 1. The kernel, in its turn, finished its boot sequence and used the secure monitor to service its secure monitor calls, and we're now able to boot the kernel on QEMU. So now let's talk about how we were able to run our own applications that are not signed by Apple on iOS, since the iOS kernel will normally only execute applications that are signed by Apple. This subject will also only be covered here briefly. More details can be found in the Black Hat slides and on our blog. So we use the trust cache in order to do this. So what is a trust cache? Trust cache is a list of executable hashes that represent the executables that are allowed execution in iOS without a signature verification. Only if the executable hash is not in the trust cache, then its signature is checked. If it is in the list, then execution is allowed. So now let's see how this works by example. Let's say we have executable 1 and executable 2. Both executables are not signed by Apple, and the executable 1 hash is not in the trust cache, and the executable 2's hash is in the trust cache. Therefore, the kernel will allow execution of executable 2 and deny execution of executable 1. So the iOS system has 3 different types of trust caches. There's a list of hard-coded hashes approved in the kernel cache. They reside in the kernel image itself, and it is hard-coded in the kernel image. So we could have just overridden some of the hashes in this list and used this list in order to allow execution of our own applications. But at first, we did not want to patch the kernel at all, so we did not choose this approach. There is also a dynamic trust cache that can be loaded at runtime from a file. But in order to load this dynamic trust cache from a file at runtime, we needed our user mode code to be allowed execution. So we couldn't do this as well. And there is a static trust cache in memory that is pointed to from the device tree. So what is a device tree? A device tree lets the bootloader tell the kernel what hardware devices are attached to the host and the specifications of these devices. In addition, it enables the bootloader to pass to the kernel other pieces of information, such as the location in memory of the trust cache. Now, the raw device tree is available in the software update, and we do patch the device tree to add the static trust cache to it, and we also patch it for different reasons. So we now see that the iOS kernel accepts a static trust cache with the list of executable hashes that exists in its memory before the kernel boot. The address of this trust cache must be pointed to by the device tree. By reversing this code, and other code that is used for parsing the input static trust cache structure, we were able to understand its structure. This way, we were able to build our own static trust cache and write it to the device's memory before booting the system. And this is the open source code of the kernel, which reads the address of the static trust cache from the device tree. The kernel later uses this address to parse the static trust cache structure with a list of hashes and builds a new structure that it can search in for the static trust cache. So we build our own static trust cache with the hashes of our non-Apple executables and use it for making the kernel execute our applications. And it works. We're now able to make the iOS kernel execute our applications using our own static trust cache. Now, since we will later see that we now patch the kernel, then we will consider to later patch core trust to just treat every application as if it is in the trust cache instead of building our own static trust cache. But this is how it works in the project now. All right, so launchd is the first user mode process in the system. It is responsible for spawning all other user mode applications and services. Now let's see how we made it execute our bash shell. So we started with mounting the RAM disk on the research computer. We used the RAM disk in order to boot the system, and at first we mounted it on the research computer. Then we removed all the files from the launch daemons directory. Now the files in the launch daemons directory are responsible for instructing launchd to execute the other processes and services. Each file in this directory is responsible for instructing launchd to execute a different process. And we added a single file to this directory to instruct launchd to run our bash shell. And we added the bash executable to the RAM disk, and we added the bash executable hash to our static crosscache. We unmounted the RAM disk from the research computer and started QEMU. So this is the file that we used in order to instruct launchd to run bash. And we can see here that we instructed launchd to run bash interactively. And here we pointed launchd to the path where it can find the bash executable on the ROM disk. And here we instructed launchd to use /dev/console, which is the serial device for stdout, stderror, and stdin. And here we instructed launchd to run bash as root. All right, so the system, actually, launchd tried to execute bash. Now, did it work? Well, of course, it did not work at first, and the logs show that there are missing libraries required for running bash. And we did not have any idea why this happened or how we can solve it. But as it turns out, the ROM disk image comes without the dynamic loader cache on it. Now, this is a file that holds most of the runtime libraries for iOS, and it holds libraries that are required for executing bash. So we decided to copy this file into the ROM disk at the correct path. This file can be found on the full disk images available on the software update. But alas, it still did not work, and it still showed the same error. So we now wanted to understand why this fails. For this, we decided to debug the dynamic loader, which is the user mode component responsible for loading the dynamic loader cache into the process. Now, since we have a GDB attached to the iOS kernel, we can just debug this code interactively and see why it fails. Okay, so this is the open source code of the dynamic loader, and using it, we can just start our debugging process from the most interesting place that we want to debug, which is this function, open shared cache file, which is responsible for loading the dynamic loader cache file. So stepping through the execution path with GDB showed that the error was here in this system call, shared region map and slide NP. Now, since the project we developed has a kernel debugger, then it makes what would otherwise be a great challenge very simple. We can just debug the user mode code and continue debugging the kernel through the system call. Now, stepping through this function, we see that the call to shared region map and slide is the one that fails. And stepping into that function, we can see that this is the condition that fails. And in our case, it seems that UID does not equal 0, and therefore the function fails. So it seems that the code tries to validate that the cache file is owned by root, that the dynamic loader cache file is owned by root, UID 0. And it seems that in our case, it is not the case. So we mounted the ROM disk on the research computer in a different way to allow permission editing, because the default way of mounting the ROM disk on the research computer does not allow permission editing. And we copied the dynamic loader cache file again onto it, and which owned it to root. And this time it worked, and we're able to run bash over launchd. All right, so now let's talk about the new content. Let's see how we're able to get access to the kernel task port from user mode. So task for PID is a machtrap, very similar to a system call that allows getting access to another task port on the same host from user mode. And when used with PID 0, it gives access to the kernel task port. Access to another task port gives full control over the other task with memory read-write code execution and everything else. And when used with the kernel task port, with the kernel task, then it gives full control over the kernel. But it seems that Apple wanted to restrict access to the kernel task port and not give user mode applications access to it. So they added a condition in this function so that if PID 0 is asked for, that is the kernel task port, then the function fails. Not only did Apple prevent access to the kernel task port, they also prevented usage of such ports from user mode with this code that gets called whenever a task port is used. In here, we can see that the task pointer is checked to see if we try to operate on the kernel task, and that the current task is not the kernel. If this is the case, then access is denied. Note that the first comparison is just a pointer comparison, and it does not check any other task attributes to verify it is indeed the kernel task. So Siguza suggested a way to overcome this. Siguza's suggestion is implementing different jailbreaks and exploits. Remap the kernel task memory to another virtual memory buffer in a different address, and create a new task port to point to this new address. This way, the pointer comparison will not detect this as the kernel task because it is in a different address and will allow access. After that, install this new task port at special host port 4, which is accessible to user mode applications. We still did not want to patch the kernel at this point, so we went on a solution similar to what is suggested on Ziguza's repository. So we allocated static virtual memory for the remap for a remapped proxy kernel task, and we used QEMU's MMIO mechanism to redirect read writes from to our fake kernel proxy task to the real kernel task. And we created a copy of the kernel task port, but instead of pointing to the kernel task, it now points to our proxy kernel task, to our fake proxy kernel task. And we installed this port to host special port 4, which is accessible to user mode applications. So now let's see how this works again with some visuals. So we allocated memory in the kernel in a fixed address for a fake proxy kernel task. So whenever a memory read operation gets to this buffer, it is redirected to the real kernel task, and the value is returned from the real kernel task using an MMIO handler in QEMU for this new buffer. It works the same way with write operations. After that, we created a fake kernel task port. We just copied the original kernel task port, and instead of having it point to the real kernel task, we had it point to our proxy kernel task. But whenever it is used, we actually operate on the real kernel task because all the reads and writes are redirected to the real kernel task. After that, we installed this fake kernel task port to host special port 4, and therefore it is now accessible to user mode applications. So this solution solves our two issues. It no longer uses the original kernel task pointer, so the pointer comparison in the function we saw before will not detect this as the kernel task, and therefore will not deny access. It also registers this new task port in a place that is accessible to user mode applications in host special port 4. And it works. Now that we execute KMEM, a tool by Ziguza that uses the kernel task port to read memory from the kernel, we can see that it can successfully read the kernel Maho header from the running kernel memory. Now, since we will later see that we now do patch the kernel, then later we might decide to change this solution to just patching these two functions. But this is how it works for now. All right, so let's see how we're able to get an active SSH connection from the host to the guest. This solution was implemented by the Aleph research member, Lev Avronsky. So there's the normal way of doing this, just by emulating networking hardware that can work with the existing iOS drivers. There is another normal way to do this with writing our own driver and emulating a network controller that can work with this driver. But we chose to do it in a much simpler way. We chose to do it with communicating with the QEMU host from a user mode TCP tunnel process using QEMU's register write callbacks. So let's see how this works. Now this is the TCP tunnel process, the user mode process running in the iOS guest. And let's see what it does in order to tunnel TCP connections from the host to the guest. So the first thing that it does is to allocate a command buffer in its own memory, in its own user mode user space process memory. After that, it allocates a response buffer. After that, it writes a receive command to the command buffer. So now the command buffer holds a receive command. And after that, it writes to a system register. In QEMU, we created our own emulated new system register that does not exist on real iPhones. We can do this because QEMU has a very good interface for system register callbacks. All right, so now this triggers the QEMU register write handler callback. And let's see what we do in here. Now, the QEMU host has direct read-write memory access to their currently mapped virtual memory map. So this makes reading from the guest user mode process very simple, even though we're now in the context of the QEMU host user mode process. We can just read directly from the guest process memory. So we read the receive command, and then since we got a receive command, we call the receive function on a host socket. And we write the received data to the response buffer. So now we have the response, the data that we got from receive in the user mode process, in the TCP tunnel memory. And after we have this, we can just send this data to a local socket and therefore transfer data from a host socket to a guest socket. So this solution is so cool and simple as it skips the guest kernel altogether and just uses direct communication between the guest user mode TCP tunnel process and the host QEMU process. So we receive data from the host socket and send it to the guest socket and vice versa. And this is how the TCP tunnel works. It is very inefficient with the busy loop running endlessly without blocking at all, even when there is no traffic available. But it works smoothly enough for now, and we have an active SSH connection. Okay, so now that we have a working SSH connection, let's talk about how we were able to get the kernel to render its kernel logs in a frame buffer instead of the serial output, and how we got QEMU to display this frame buffer. So this solution was implemented by the Aleph research member, Vera Menz. So the first thing that we did was to set up a new ROMFP device with our own display parameters in QEMU. And we had to tell it the frame buffer height, width, size, address, pixel format, and everything else. The iOS kernel has built-in support for rendering the console output messages to a frame buffer instead of writing them to a serial device. So we just have to configure the relevant boot arguments with the frame buffer size, height, width, pixel format, memory address, and everything else, and make the kernel render these messages to a frame buffer. After we did that, the kernel started rendering these messages to the configured frame buffer. And here you can see the code that actually that actually puts this, that configures the kernel to use this frame buffer. So after that, we just had to connect the QEMU ROMFB device frame buffer to the iOS frame buffer, and it works, and we can now display in the QEMU window the rendered frame buffer. Okay, so now let's talk about our block device driver. So the ROM disk that we used until now to boot the system, the ROM disk block devices do not support disks that are larger than 1.5 gigabytes. But the full disk images are larger than 4 gigabytes. Plus, using the ROM disk, we only have support for loading one block device in the system. But we wanted a block device for the root mount and another one for the read-write data mount, same as a regular iOS system. So to solve this, we wrote our own block device driver to load the two large block devices. And now we had to patch the kernel and call our driver during the kernel boot. And we had to do it this way because we needed our block device driver to be up and running before the kernel mounts the root mount in order to use our block device. We tried to solve this in a few ways without patching the kernel and spent quite some time on it. But eventually we decided at this point that it is now time to patch the kernel and solve it this way. So first, let's see how the kernel, how we hook the kernel. So we allocated kernel memory at a fixed location, and we wrote a trampoline hook code in ARM64 assembly and copied it to the allocated kernel memory. Then we compiled our driver code, read it in C, to a flat ARM64 binary, and we also copied it to the allocated kernel memory. We then parsed the page table and made all these pages read, write, execute because they hold our driver code and data, so we need read, write, execute. All right, so let's say this is the kernel code, and this is the place where we want to install our hook. And so now let's first see if this is a good candidate for us to install our hook in. So we want to install our hook here. And we need to make sure that there are no position-dependent instructions because we will now override 3 instructions and we will later execute them from a different location in memory. So we need to make sure that there are no position-dependent instructions such as ADR, ADRP, and branch instructions. And we also need a register that will be discarded after the hook because when we override these instructions, we will also use one register that we will not be able to restore its value later. So this looks like a good candidate because it answers these two conditions. We have no position-dependent instructions here in these three instructions, and we have x1 that is discarded after the hook. So let's install our hook here. So the first thing that we do is to copy the original instructions to a different memory location where we will execute them later. And then we overwrite the original instructions with new instructions, and these instructions are just responsible for loading x1 with the hook code address and then jump to x1. So this is how it works. And then the hook code saves all the registers on the stack, set up x1 to point to the driver code, and then jumps to the driver initialization code. Once it returns from the driver code, then we restore all the registers from the stack. We execute the original three instructions. We set up x1 to point to the kernel code after the hook, and we continue executing the kernel code from where we stopped. Okay, so now that we're able to hook the kernel, let's see how the driver itself works. So we do not have a kernel development kit for iOS or a compatible C++ compiler. So in IOKit, each driver is represented by a C++ class, and for each class, the iOS CPP runtime has a meta class used mainly for runtime type information. To create a new block device driver in IOKit, we needed to create a class inheriting from the IO block storage device class, implement the relevant virtual functions, create a class instance, and register it in the IOKit registry. For this, we decided to create a new class with C code that does exactly this. So the first thing that we had to do was to create new vtables for the new class, for the class that represents our driver, and its meta class. After that, we called the meta class constructor and registered the new meta class instance in the global IOKit classes dictionary. After that, we called a static function alloclass with name and used it to create two new instances of our driver class to represent our two new block devices, one for the root mount and one for the read-write data mount. After that, we called register service on these two instances in order to enable the new block devices. Now, this is what a regular IOKit driver and the iOS C++ runtime would have done to register the classes and to register their instances. So again, in IOKit, each driver is represented by a C++ class, and for each class, there is also a meta class. For our new classes, we copied the vtables of the class and its meta class and created our own vtables with our own virtual functions. For the meta class, we implemented the alloc virtual function, and we will get to that later. We changed a few virtual functions for the class itself, but we will only talk about one of them to explain how this works. The virtual functions, indices, and roles were examined by reversing other classes that inherit from the IO block storage device in the kernel and their virtual functions. So this is the driver bring-up code, and we just saw how we created the two new vtables. After we create the two new vtables, we call the metaclass constructor to create a metaclass global instance. And the inheritance data is actually used here in the metaclass constructor call and saved in the metaclass global instance. After that, we register the metaclass instance in the global IOKit dictionary. And after that, we create a driver instance. Now, the creation function finds the driver class by name by searching this IOKit global dictionary where we just registered our metaclass in. So this is why it is important to register the metaclass global instance in this global IOKit dictionary. Now, this triggers the alloc virtual function for the metaclass that we overwrote before. So let's see how we implemented it. The first thing that it does is to allocate kernel memory for the driver instance. Then it calls the parent constructor. After that, it fixes the vtable pointer to point to our new created vtable. After that, it calls the instance constructor on the metaclass instance. Now, this is what gets called every time a new C++ class is created in the iOS kernel. All right, so now we have a driver instance. Now, in IOKit, every driver needs to be registered in the IOKit registry in order to be active. The IOKit registry is a tree of driver nodes that each one is connected to a parent driver. In our case, it doesn't matter which node the driver is connected to. So we find an existing registry node, and we attach our driver to this existing node. And then we call register service on our new driver instance. Now this triggers the IOKit runtime to actually find its own drivers to attach to our instance. And these drivers are responsible to create the two new BSD block devices. And after that, we have two new block devices that are actually active and ready to be used. All right, so now that we have our block devices active, let's see how we read and write from them. So we implemented the virtual functions to read-write from to the new block devices. And this works in a very similar manner to how the TCP tunnel works. We write to a system register, and the QEMU callback read-writes directly from two memory buffers on the guest to transfer the data. The block device data on the QEMU host is backed by files. So this is the virtual function responsible for read and write operations for the block device. Same as the TCP tunnel, we again use the QEMU system register callbacks mechanism with our own non-existing system register. And we again use the fact that QEMU has direct access to the currently mapped virtual memory map. Now this is an example of how the read operation works. So again, we allocate a command buffer in the kernel memory. And we allocate a response buffer in the kernel memory. And we write a read command to the command buffer. So now the command buffer holds a read command. And we write to the system register. And this triggers the QEMU register write handler callback. And in it, we can just read directly from the command buffer. So we now read the read command. And we perform a read operation on the file that is backing the block device. And we write the response to the response buffer. So now the function, the read virtual function of the block device can return these data and operate properly. And here we can see the IOREG output in our system, and we can see that we have our driver loaded and active. And here you can see a successful mount command for our new block device on /mnt1, and we can see that it actually holds real data on it. All right, so now let's talk again about the secure monitor. So we moved from not patching the kernel at all to patching it in order to load our driver. But in order to do this, we have to disable the secure monitor in order to disable KPP, right? Because it will not allow us to patch the kernel and to patch the page table. But we have the secure monitor call that we want to not load the secure monitor and just start executing the kernel at its entry point in exception level 1. But we have the secure monitor call instruction that we crashed on before when we did just that. So there's another simple solution. We just snap the secure monitor instruction, and therefore we can continue execution. But there's another way KPP kicks in, and it is by trapping floating point operations done in user mode or in kernel mode to the secure monitor, to exception level 3. But this is configured by the CPA-CR-EL1 register. So if we just intercept all writes in QEMU, we just intercept all the writes to this register, so it will always hold this value. And this value means that FPENE3, that means don't trap any floating operations at all. Then the KPP never kicks in, and the secure monitor is never triggered, and then we can just execute our kernel without the secure monitor. Now, if you want to learn more about how this works, how KPP and the secure monitor works in iOS systems, and this is a great, very good blog post with all the information. All right, so now let's talk about some launchd craziness we encountered. So we created our two raw HFS block device disk images with the full disk images content from the software update, one for the root mount and one for the read-write data mount. And we started QEMU again, but instead of having it we pointed it to the new block device for the root mount instead of having it mount the RAM disk as the root mount. And we added our launchd items for executing our bash shell, to start our TCP tunnel, to start our dropper SSH server, and other services. We added them to the launch daemons directory, as we saw before, where all the launchd items are saved. But when we started the system, our services did not run. But we saw that all the original system services did run. But we did not have any idea why this happened or how we can solve it. So we tried a few things. We tried to remove all the launchd items, all the files from the launch daemons directory. But still no go. We see that all the original iOS services still execute same as before, and obviously our processes don't execute. So we tried to remove the launch daemons directory altogether. But this time we get a panic and nothing executes. So this time we tried to boot with the content of the RAM disk. We tried to boot using the new block device, but with the old content that we used to boot the RAM disk with, just the same as before. But this time we got a panic with an error about a missing service cache. So in order to understand this, we reversed launchd, and we saw that there's another file, another place where the launchd items are saved. xpcd cache dynamic library. So this is the service cache that was that the message referred to before. And it seems that this dynamic library has its own data structure which holds the launchd items instead of using the launch daemons directory. And it looks like launchd decides whether to use this cache or the file system, this service cache from the dynamic library, or the file system launchd items from the launch daemons directory based on the boot arguments. If launchd thinks this is a ROM disk boot, then it allows loading launchd items from the file system. Otherwise, it can only use this dynamic library. So this is the code where launchd actually decides whether it is a ROM disk boot or not. If it can find rd equals md0 in the kernel boot argument, then it thinks it is a ROM disk boot. Otherwise, it's not a ROM disk boot. So we just patched the launchd to make it think it always finds rd equals md0, and therefore it thinks it is a ROM disk boot, even though it's not a ROM disk boot. And we signed our new launchd patch binary, and we updated our static trust cache to include the hash of the new signed binary. And we replaced the launchd binary in the file system. We removed the service cache dynamic library file from the system, and now it works, and launchd uses our launchd items from the launch daemons directory. And we can see that we have our bash process running, and we have Springboard, and we have our TCP tunnel, and we have our dropper SSH server. All right. Okay, so now let's talk about what lies ahead for this project. So we want to implement GUI and HID support. We want to understand SEP better and actually execute keybackd that we just disabled for now. We want to implement interrupt support for performance improvement for the TCP tunnel. We want to test a VPN connection over an SSH tunnel. We want to implement a few performance improvement. We want to use KVM virtualization instead of emulation. We want to see if to investigate using more than one CPU. And once we get GUI support, we want to understand if software rendering is fast enough or we need to do something else. We want to support more iOS versions for more iOS devices. We want to work on symbolication with Jonathan Levine's JTool or otherwise to support more iOS versions. We want to implement fast state recovery. And of course, the main motivation for starting this all was to conduct security research, and we intend to do just that. And we intend to do fast coverage guided structure with state recovery fuzzing. Now, if you found this project interesting and useful, you can find it on GitHub. And better yet, you can contribute code to it on GitHub. Have a look at the issues to tackle posted on the GitHub repository. If you indeed found it interesting, you can find more research details which I did not have time to present, and other research projects on our blog and on Twitter. We will soon update the code, the blog, and everything with all the new content that was presented today. And that brings us to the end. I'd like to thank you all for your time and attention today. Thank you.
Anybody has questions? Questions? No questions? Oh, there we go.
Hey, thanks for the talk. So, have you tried running QEMU on an ARM host, and did it improve like your performance and stuff like that for fuzzing, or did you try it and did it help?
Um, Well, actually, yes, we just started working on it, but it's a very weak ARM processor. So, and of course, when doing it in full emulation, then it gives no performance improvements because it still uses emulation. But when we try to do it with KVM, it seems to be running a little bit quicker, but KVM, the system still does not run very well on KVM. We have to solve a few issues. So once this happens, we think we will see some performance improvements.
Okay, thank you very much.
Anybody else? Questions? Over there.
So you mentioned intercepting knopping out the SCM calls and then intercepting some of that. Do you have any projection of like what impact that'll have on the security context of it? Is there any like testing that you can't do because that might catch you, or things that might you know you might be able to do in an emulated environment that may not translate to hardware because of the modifications you've made there?
Mm, well, there could be things like that, but not that I can think of right now. We just use it to disable the secure monitor and the KPP. So exploiting vulnerabilities will be easier on the emulated system than on real devices because you don't have to. I don't know if you depending on the device you try to attack. There's KTRR or this KPP mechanism using the secure monitor. So exploiting will be easier, but as for finding bugs, I can't think of anything.
Anyone else? Oh,
Hi, great talk. Why is there a 1.5 gigabyte limit? What's up with that? Where does it come from? And why can't you just increase it instead of doing that whole voodoo stuff with the block driver?
So actually, the system behaved very strangely when we tried to load larger disks on the RAM disk, and it actually loads this block device in a special mechanism. It does not use a full IO-Key driver loaded for this block device. It just creates the BSD block device in the system. And to be honest, it didn't fail to mount larger disks. It mounted and then it behaved very strangely. And instead of investigating it, we just decided to implement our own block device driver.
yep.
Thanks for the talk. Would pointer authentication be difficult to add to this project? Like, does it already implement that, or is that going to require a lot of extra effort to add to it? Or?
Um, so well, we started to think about this, but we still haven't really looked into this. It depends on a few factors. If we do it with emulation, then it depends whether QEMU currently supports pack instructions in a way that is compatible with how Apple uses them. Otherwise, we'll have to do modifications in order to emulate it. And when using virtualization, then we'll have to use a processor that supports these instructions in such way or to do other modifications to support it. So, yeah.